Hello everyone, and thanks for watching my videos. Today in this video, we'll be covering the fundamental of solution chemistry. We're going to be looking into the different types of solutions, how solutions are made, what energy involves in making a solution. So I hope you enjoy the video, and without further ado, here's the video. Thank you.
This homogeneous mixture, you have to have a solvent, which is a major component. And you have to have a solid, which is, again, you can have more than one solute, but at least you need a solid and a solvent. And the solid is the minor component. And we can have different state of solutions depending on the type of solvent and solute, as I explained last live recordings. We also talked about the chemistry of the solution, how you have to break the intermolecular forces between the solvent and the solvent, the solid and the solute, and you need to form a new intermolecular forces between the solid and the solvent. We looked also into the energy change in a solution. Since we are looking into separation of molecules, to separate the molecules, that means you have to provide energy. So this is an endothermic process. To separate the solvent molecule, you have to provide energy, which means it's an endothermic process. Every time you require energy, then it's an endothermic. Every time you release energy, that will be exothermic. So we have an endothermic processes and exothermic process. The endothermic processes are the separation of solid molecule, the separation of solvent molecule. And here are the description of each of these energies. Solvent-solvent interaction, solid-solid interaction, and solvent-solid interaction. Two of them are endothermic, which mean positive delta H, and the solvent-solid interaction is exothermic, which is negative delta H. And we did look into this diagrammatically, as represented in here. The left-hand side represented the exothermic delta H of solution. As you can see, the negative is exceeding the positive. And on the right-hand side of this screen, you will see the opposite, which is basically the negative is less than the positive combined, which indicate an endothermic process. And this can be directly measured through the temperature of the solution. So you can basically predict what's happening by measuring the temperature. If the temperature increased as a result of dissolving that solid in water, what does this tell you? It tells you that you're in this scenario here. When the temperature increased by dissolving the solid in water, that means this is an exothermic process. If the temperature decreased by dissolving the solid in water, that tells you that you're in this process here. So from just looking at the temperature change, as you are adding the solid to water, you will be able to tell which processes is taking place. Is it exothermic or endothermic of this chapter? So the new content is really still continuing on the solution. This chapter is all about solution. So since we're talking about adding solid to water, how far we can keep adding solid to water? We reach what's called saturated point. When you reach the saturated point, this is how much solute can be in solution. And you can go beyond this saturation, but that becomes super saturated. So if you add more solid, by increasing the temperature to dissolve that solid, you are creating a super saturated solution. And that is containing more than the equilibrium amount. So you exceeded the equilibrium amount. You exceeded the amount needed to make the saturated solution. It comes from its name, super saturated. So saturated solution, you have the equilibrium amount. Super saturated, you have more than the equilibrium amount. And the super saturated is going to precipitate it out. It's going to basically, if you cool it down, you will see the solid are precipitating out of the solution. The unsaturated, by its name, it's containing less than the maximum amount. So this is some terminology on the solution. You have a saturated solution, which contains the maximum amount, the equilibrium amount. You have unsaturated solution, which contains less than the maximum amount. It's called unsaturated, is not saturated with solid yet. And then the supersaturated. So here is the supersaturated. The supersaturated is containing more than the equilibrium amount. And once you cool it down or add an additional solid, you will see the solid is coming out, and this is coming out as crystals. This is really unique process. And we use this process in purification of solids, different, especially organic solids. So you will see them as they come out as needles, as you can see here. And again, so this is known as crystallization. All right, so this is again the different types of solution. So we have saturated solution, unsaturated, and supersaturated. Solubility depends on the solvent and solid. And always remember this, like, dissolve like. Like, dissolve like. What does this mean? It means if you want to dissolve an ionic solid, you dissolve an ionic solid in a polar solvent because they like each other. They're going to communicate with each other. Remember, in order to have a solution, you need communication between the solvent and the solute. The solvent has to communicate with the solute. Water cannot mix with oil. Why water cannot mix with oil? Because there is no communication between the water molecule and the oil. What is a communication? The intermolecular forces. There is no intermolecular forces between water and oil. Oil is non-polar, water is polar. So again, they don't mix with each other. What is going to mix in oil? Non-polar. If you have a non-polar solute, it will dissolve in oil much faster, again, compared to any other solute. So here is an example, just to show you the solubility in polar. So water is a polar solvent, and solubility in hexane, which is a non-polar solvent. So this is polar solvent, this is non-polar. How do I do this as non-polar? It's carbon hydrogen. Remember, carbon hydrogen is non-polar. So this is a non-polar solvent known as hexane. We use this a lot in organic chemistry. This is water, which is again highly polar solvent. So here is alcohol. The different type of these alcohols is the increasing of the alkyl groups. This here is carbon hydrogen group. So as you can see, the more you increase them, the more you increasing the non-polar side. The more you increase this, the more you increasing the non-polar side, because remember, carbon and hydrogen are non-polar system. So the more you increase that, the more you increasing the non-polar. And look at the solubility in water. I want you to notice that. For having a CH3, the solubility is infinite. So you have an infinite solubility in water for methanol. The same thing for ethanol. You're having an infinite solubility. So you have a very high solubility because you have a very small, again, non-polar group. Propanol, you still have an infinite solubility. Now you increase the carbons beyond 3. Now look at the solubility. Now you have a limit. The solubility is 0.11. And this solubility is moles per 100 grams of water. So this is how many moles per 100 grams of water are soluble. This is, again, increase the number of carbon atoms. Look at the solubility decreasing as you increase the number of carbon atoms. So one more time. Like, dissolve like. This one has a lot of polar side. The hydrogen bond, this is very small, so the non-polar side is less. We always, if you recall, we have a substance that we call hydrophilic. Hydrophilic means like water, and we call substance that call hydrophobic, mean doesn't like water. The hydrophilic is the polar side. The hydrophobic is the non-polar side. So here, this methyl group or this carbon hydrogen is a hydrophobic side. A hydrophobic side doesn't like water. The OH is a hydrophilic side, which means like water. So the more you increase this hydrophobic side, the more you decrease the solubility in water, as you can see here. The opposite will be for the non-polar. Look at the non-polar. The methanol has the least solubility. Why? Because this one doesn't have a high hydrophobic side. It has mainly the polar side, OH. You increase the carbon atoms, you increase the solubility. As you can see, you have infinite solubility for all of these. So this is, again, just a direct example to show us the solubility and what will increase the solubility between two components. So why alcohol? Again, why alcohol have this high solubility in water? Because of the hydrogen bond. Like, dissolve like. Both of these has, again, look at the hydrogen bond between the water and the alcohol. So the hydrogen bond will be created between the water and the alcohol, and that was going to increase the solubility of the solution. And again, because of like, dissolve like. So having a higher intermolecular forces between the solvent and the solute is going to increase the solubility. The same thing as we did with the ion dipole. A higher ion dipole interaction is going to increase the solubility. So this is how alcohol communicate with water. So the hydrogen bonding. Oil cannot communicate with water. How oil is going to communicate with water? Oil is non-polar, water is polar. There is no communication between them, and that's why oil will not dissolve or mix with water. I mentioned increasing the temperature will increase the solubility. So again, adding solid to water and increase the temperature is going to increase the solubility, which makes sense because you're going to break the crystal system. The temperature is going to provide, again, additional basically energy to break the lattice energy. So increasing the temperature is a trend to increase the solubility in solids. So what are we focusing today? This is our focus today, is how to determine the concentration of a solution. Since we're already dealing with a solution, when you deal with a solution, you're mixing two components. Does it matter if I have 10 grams of sugar in water versus 20 grams of sugar in water versus 30 grams of sugar in water? The answer will matter. The concentration will be different. Having 10 grams of sugar in water versus 20 grams versus 30 grams, you are increasing the concentration. So how can you measure the concentration? You're looking at the units that we need to know in this course. These 4 different units. Molarity, which is moles of solute per liter of solution. Mole fraction, which is the number of moles of one component divided by total number of moles. So this is moles. So this is deal with moles. This is deal with moles and volume. Mass percent. This is deal with the mass of one component divided by total mass times 100. So the mass percent is the mass of one component divided by total mass of the solution times 100. Molality is moles of solute per kilogram of solvent. So this is specific for solvent. This is specific for solution. The two main unit is molarity and molality. So these are where, all right. So here's the equation. All what you need to do is to determine the moles and determine the volume of the solution, and that will get you the molarity. For the molality, you need to determine the moles of the solute and the mass of the solvent, and that will get you the molarity. The units is very important. The mass of the solvent is in kilogram. The volume of the solution is in liters. So this is a very important unit. They have to make sure that you count when you're doing this. So here's an example. The best way to understand this is to go over an example. Assuming that seawater is an aqueous solution of sodium chloride. That's the seawater is an aqueous solution. What is its molarity? So what would be the molarity, which is this one here? What would be the molarity of seawater? Knowing that the density of seawater is 1.025 grams per milliliter at 20 degrees Celsius, and the sodium chloride concentration is 3.5 mass percent. So it did not give you mass, it gave you mass percent. So it's already have this already embedded. So the mass percent is going to always show up in our concentration calculations. So how you interpret the mass percent, how you go from there, from the mass percent. Every time it says certain value, mass percent, that means you have this much grams in 100 grams of solution. So based on this, we have 3.5 grams of sodium chloride in 100 gram solution. So every time you say 5% by mass, what this mean? Mean 5 grams of the solute in 100 grams of the solution. When it's tell you 10% by mass, what this mean? 10 grams of the solute and 100 grams of a solution. So we always have the mass, we always have the percent out of 100. And when it says mass percent, that means it's by weight. When it say volume percent, that means by volume. So depending on the unit that's saying, you will be able to know what do you have out of that solute. We're going to be using mass percent, which means this is in grams, 3.5 grams in 100 grams of a solution. So if you have 3.5 grams of sodium chloride, how many grams do you have out of water? Remember, the seawater is a solution between the sodium chloride and water. So if you have 3.5 grams of sodium chloride, how many grams you have out of water? 100 minus that. So that will be 100 minus 3.5, and that will be 96.5 grams. So this first, again, line here, just explaining the word the 3.5 mass percent given. Okay, so I hope everybody understood how to express the mass percent. So when it says 3.5 mass percent, that means it has 3.5 grams of the solute, which is sodium chloride, in a 100 gram solution. And if you have a 100 gram solution, what will be the mass of water? 100 minus 3.5, and that would be 96.5 grams of water. So now what do we have? We have the density of the solution. How you get the volume? You need the volume of the solution. How you get the volume of the solution? You have the mass of the solution, which is 100, and you have the density of the solution. You can get the volume. The volume is going to be the mass divided by the density. So again, so we have 100. So to get the volume, you will divide by the density. If you look at here, it's a cross multiply. If you cross multiply, you will see the density times volume equal mass. So from here, the volume will equal mass over density. So here's the mass. Here is dividing by the density. Why did we need to divide by 1,000? Because remember, this volume will be in milliliter. So up to here, up to this part here, the volume is going to be in milliliter. So you have to divide by 1,000 to get the volume in liters. So this is the first part of the calculation. You're trying to find the volume of the solution. To get the volume of the solution, you need to be in liters. Once you get it in milliliter, you divide by 1,000, you will get it in liters. So this is the volume. How you get the number of moles of solid? You have the mass of the solid, 3.5 grams. You have sodium chloride, 3.5 grams. You divide by the molar mass, you will get the number of moles from Chem 101. To get the number of moles, you divide the mass by the molar mass. Here is the molar mass of sodium chloride. And that would be the moles, and that would be the volume. So this is how you answer this question. This is a standard procedure, as you can see here. The example will be different, but this is how we approach this kind of calculation. Molality. Molality is much easier than molarity. So calculation of molality is a more straightforward than molarity. Why? Because you have solute and solvent, and you can always separate between both of them. You can always know what is the mass of the solute and the mass of the solvent. So here's another example for the molality of the solution. What is the molality of a solution prepared by dissolving 0.385 grams of cholesterol? Here is the formula of cholesterol. In 40 gram chloroform, here is the formula of chloroform. So we are looking for molality. If I'm looking for molality, here is the equation. I need the moles of solid. Do I have the mass? Yes, I have the mass of cholesterol. Do I have the formula for cholesterol? Yes. So I can determine the molar mass. Here is the molar mass of cholesterol. 386 grams per mole. So the first part here, I can determine immediately. All I need is the moles. I have the grams, and I have the molar mass. What is the second part? Dividing by mass of the solvent in kilogram. Do I have the mass of the solvent? Yes, the mass of the solvent is 40 grams. All I need is to divide by 1,000 to convert it to kilogram. So I have, as I said, it's a more straightforward. You already got the moles and the kilograms immediately from the information given in the problem. So one more time, it's asking for molality. Molality is moles of solute per kilogram of solvent. So do we have the moles of solid? No. Do we have information to get the moles? Yes. I have the grams of cholesterol, which is the solute. You can tell from the mass. Look at that, 0.385. The solvent is 40. You can see the difference here between them. So 0.385 grams divided by the molar mass. How can I get the molar mass? You are giving the formula. 27 times 12 plus 46 times 1 plus 16. So you have the atomic mass, you have the formula, you will be able to determine the molar mass. Dividing 0.385 by 386, that will give you 0.00997 moles. So this is the moles based on that. Now the solvent. Do I have the mass of the solvent? 40 grams. Dividing the 40 grams by 1,000 will convert it to kilograms. So this is why the conversion needed. Now, do I have the moles and the kilogram? Yes. Divide the both of them, and you'll get the molality.